Well, thank you so much. Thank you so much, everyone. As you heard, it's not my work, but I try to do my best. So please forgive anything that happens in between. But so the good thing with this, actually, I was lucky because I thought, oh, I have to talk so much about like privacy and genome. But then Jean-Pierre today morning took care of the job for me. So I don't think I need to spend too much time about the necessity for privacy preserving considerations when it comes to genomic data. But these two folks that I know chose this particular type of computation and then said, okay, well, there's so much that you can do with genomic data. Let's focus on only a very limited number of type of computation. Particularly, they chose non-medical related computation. By medical, I guess they meant things that are not related to diagnostics. So they chose ancestry test, paternity test, and genomic compatibility test. And so ancestry test, the idea is okay, two people want to figure out whether they're somehow related or not. Paternity, you know, you might have seen, if you especially watch American TV shows, you know, there's like the test that, oh, you're not the father, you know, and then the guy jumps up and starts dancing. And, and genomic test is like basic, genomic compatibility is basically Alice and Bob are like, have been dating for a long time. They're ready to take the next step, but they want to make, since they're very educated, they want to make sure that the child or children that they're going to have will not have any disease. So they want to run some compatibility to figure out that they don't have any disease. Right? So these are the computations that the focus of this paper was about, right? So now the idea is like, as I have been talking about, you know, in secure computation, you usually divide into two categories, two-party, multiple party, right? Multiple party is easy, you know, is easier, I should say, because you jump immediately, you dive into secret sharing and start talking about secret sharing, verifiable secret sharing, and you try to do all those things that we know a lot. And we had Shermont earlier on, right? Two-party, well, things are slightly different. Here, two-party is better because, as I have been saying, Alice and Bob. So it makes sense to focus on two-party. The only thing is that to be different, in this paper, they decided to have a server, like just what Ostap was talking about, somewhere there, right? So the server is going to help, right? So it's a server-aided two-party computation. Now, the assumption here they're making is that at least one of these parties is quite weak, right? Computation-wise and communication-wise. Let's say Alice, she doesn't want to participate too much, you know, and so when you're trying to come up with a solution, you have to make sure that, you know, you're not putting too much burden on at least one of them, right? And you are trying to leverage the server, the aided server, as much as you can, right? Well, I guess I can skip all of these things. Jean-Pierre said it, the SNPs, what they are, you know, what the particular type of alphabets that they come from and everything. And STRs are something different. These are usually used for paternity tests, right? So STRs are basically a list of tuples, and if I'm your child, for each tuple I should have one of those two is a pair. One of those two that you have, I should have it, right? It's because one comes from mother, one comes from father, right? And so, and by the way, I don't know what STR stands for, something, right? So ancestry, what you're trying to do, you're trying to compare it to SNPs and figure out the intersection, right? And if there is bigger than something, then you say, okay, you guys too close, we are related somehow, right? Paternity, as I said, you try to look at the STRs and say, okay, well, there should be intersection for each pair, and if that happens for all pairs, then, you know, that guy is your father or mother, right? And compatibility tests, basically, there are different type of methods suggested or offered by folks at the genomic area and field. And at the end of it is either you go the approach of STRs or SNPs, right? So you can't talk about privacy-preserving computation without bringing up your security model, right? That's the first thing that you have to do, right? So these guys said that, okay, what is our model? And when you define your model, you have to spend a good time justifying it, right? So why I chose this model. Somebody here was talking about two different types of adversaries, semi-honest and malicious, right? Stop. Thank you. It's the advantage of going last because someone else talks everything for you. So semi-honest, the idea, as Ostap said, is basically the adversaries are going to execute the protocol I just said very quickly, right? And they don't deviate. Malicious, they can deviate. They can do everything they want to do. And they can actually, they don't have to provide the inputs that they're supposed to do, right? So that's actually a big deal. So think about it. The inputs could be anything. They can do whatever they want. So they're up to go, right? So they can do tampering with the input. And these guys said that, okay, for our computations, we try to justify our choices. In the ancestry test, they decided to choose semi-honest for the Alice and Bob, right? So the idea is that, they are relatives. So they're not enemies to each other, and that's how they justify. They said that, we're going to say that most likely they just want to figure out whether they're truly relatives or not, or have good intentions. Paternity, I don't need to talk about much about it. Malicious, right? Yeah, if you watch the shows, that dance when they hear that they're not the father, that explains that they want to basically change the results, right, in their own benefit, right? And genetic compatibility for disease, like you're passing on to your children. Also, malicious is a good idea. Think about it. Because that type of computation is a computation that can reveal information. So I can pretend to have early signs of Alzheimer to figure out that whether you have it or not, right? And if the answer comes out to be yes, then I know that you have it too. So I can fake my input to basically figure out something about your thing, right? So in this particular type of application, when you boil it down to the genomic computation, it makes sense that actually not only you have to assume that the parties are malicious, but on top of that, you have to assume that they may actually input, or they may change their inputs, or tamper the inputs, right? So you have to have some sort of verification that the inputs are actually proper, or they're not done in any particular bad way. Again, where is Ostap? He talked about Garble circuits, but again, I quickly mention it. When you talk about two-party computation, the first two things or three things that come to your mind is one of them is homomorphic encryption, that usually is expensive, is too slow. And the other thing is good old Garble cycle from Yahoo's time all the way till now. And there has been a lot of work to improve it and make it more efficient and all of that. So I'm going to very quickly jump over it because he had a very good slide there that you can represent your function with Boolean gates. And basically, for each wire, you can represent the inputs of the wire with labels. And someone will generate the whole circuit with all the labels. And that guy will be called a generator. And the other guy will be called evaluator, will basically engage with the generator in the computation and says, okay, give me the labels and I will evaluate the function and go down all the way at the end of the circuit and figure out the labels for the output, right? And that type of computation, as you heard it earlier on, involves oblivious transfer, right? And you must have heard that is actually costly protocol. So you want to get rid of it. It relies on public key operations, and the less you do that, the better, right? And okay, so that's oblivious transfer. I think I can skip that, right? So let's go to the protocols that these guys offer, or they provide these protocols. Number one, ancestry test. So the assumption here is that Alice and Bob are relatives, so they're semi-honest. Now they're using Garble circles. Now if you think about Garble circles, there has been lots of papers that in Garble circles, the circuit generator has to be, most times it has to be semi-honest, but the evaluator can be malicious. I mean, you can have both of it malicious too, but that would be very complicated. But in the general case, the generator can be semi-honest, and then the evaluator can be malicious. So in this case, they assume that, we can actually assume that this guy over here, the server, is actually malicious. So Alice Bob, semi-honest, server malicious. And I think this is the protocol that they came up. And the good thing about this protocol that they came up is that this is a garbage SQL evaluation with no oblivious transfer. So it's quite good. But it's very easy in concept. So you think about it is that one guy, let's think about that Bob is a guy that can spend more time than Alice. Well, one guy will generate the circuit and sends it to the server. And Alice will only send her own, the labels that correspond to her own input, and send all of that to server. And server finishes the computation, finishes the garbage circuit, and then sends the outputs. And then they both happily, in a fair way, figure out the output, right? And no oblivious transfer quite fast, right? But too easy, right? So I'm going quickly to the more interesting one. When Alice and Bob are malicious, so since they're malicious, they can be in charge of generating the circuit. So who's going to generate the circuit? The guy who is semi-honest, which in this case, server, right? So the server is going to generate the circuit, and now what's going to happen is that Bob is going to jump in and says, oh, well, I'm going to be the evaluator. And now you can't avoid the oblivious transfer, so oblivious transfer will come in, and the size of the oblivious transfer protocols that you're going to execute is the size of the Bob's inputs, right? And Alice will just pass her labels to Bob, right? And now Bob is the evaluator. He's going to run the circuit, and then he's going to figure out the labels for the output. He's going to give it to Alice, all those labels. Now Alice has to figure out that, okay, these are actually truly the labels that correspond to the output, so she needs some sort of verification method, and what she's going to say is she's going to ask the server. Says that, okay, give me something. So then I will be satisfied that these are actually truly the outputs, right? That is coming from running the circuit. So what the server would do, because server has all the labels, will hash the labels for each wire, output wire, permute them, send them to Alice, and Alice will just have to do a simple exact match of the hash of the labels with everything that she got from the server, right? And so that will take care of it. And again, these guys prove with simulations and everything that why this is secure with respect to malicious parties and everything. Now they spent a good time on something that initially was difficult for me to understand, but to be honest, to give you a confession, but I read that they go a step further for the compatibility test. They actually introduce input verifications, right? So input certification, I would say, right? So now here you have to rely on another party, the party that like is a trusted party, I don't know, like NIH or someone, that can actually issue signatures on the inputs, right? On the bits of the inputs, right? And so these, Alice and Bob, will have the signatures, and all they have to do right now, with the help of zero knowledge of proof and some sort of zero knowledge proof and commitments, they can actually show that the labels that are providing into the circuits are actually truly correspond to the inputs that they hold the signature for it. Signature from a trusted party, right? Ooh. And so then what they did, so they have all of that, and then they implemented their things, right? So they implemented for the ancestry test, and I think, if I remember correctly, they had i5, three machines, Red Hat i5. They just used one core, and they had a very fast LAN connection between three of them, right? So communication delay was negligible, right? And for Ancestry, they had 2 to the 17 and SNP. They didn't just choose that out of nowhere. They looked at the genomic research, and they saw that's like a typical size. And anyway, they implemented, and so basically this is the result that you can see. Execution column, you know, offline, online, you heard about it. Offline, you can do it separately, locally. Online is when parties are interacting with each other. And so you can see the pretty fast, right? And communication is basically just the size of the labels and the circuits that they're sending to the party. And then they did that for paternity test, but no, look, paternity test has oblivious transfer, but only one party is doing it, right? So Alice is completely gone now, she's asleep. And Bob's majority of computation happens at oblivious transfer, so that's the bottleneck, right there. And communication kilobytes, so that's good, right? And then they did for general compatibility, now they brought the signatures and zero knowledge proof of knowledge, and all these times are, I believe, in seconds, milliseconds, sorry. All these times are milliseconds, and all the communication units are kilobytes, right? And so zero time, okay. I just say that at the end of their paper, when you read it, they actually implemented all sorts of computation with the matrix multiplication, Hamming distance, a bunch of other things. And anyway, their claim is that, okay, we are not the first people who came up with the idea of using server-aided computation, but they show in their complexity table that their complexity beats everybody, right? And they have the fastest, right, with that. And yeah, you can go and read their paper, and easy questions.